ladies and gentlemen, class recording has started. So, over the past couple days, we've been talking about these ideas of electric potential energy, voltage, and current. So just as a reminder, right, we said that anytime we discuss voltage, that's synonymous with energy, right? We talked about increasing the energy of charges, and we go from there. Current, on the other hand, is the movement of charges, or how many charges we're talking about. And yesterday, we went through and we looked at these four pictures, right? You know, low current, low voltage, high current, low voltage. We talked about the differences between those four, okay? There's one more piece to this puzzle, because we said that really this unit here is about getting charges to do what we want them to do. Energy is the ability to do stuff. So how do we harness that energy? How do we get it to do what we want it to do? There's one more piece to this puzzle, and it's called resistance, all right? But to really understand resistance, we actually have to go back to the first outline that we did, the one that says electric charge, electric force, and electric field. And if you look, I believe Roman numeral number 2 says conductors and insulators, right? We didn't fill that out and we went through, okay? So let's talk about that here. Okay. First, let's talk about conductors. I think most of you are aware that metals make good conductors, and conductors allow electricity or heat to flow through them pretty easily. When we talk about why metals make good conductors, we have to go back to our discussion about valence electrons. Remember, valence electrons are on the outside part of an atom, and overall, atoms are looking to get 8 valence electrons. And we looked at some pictures of like sodium, and sodium, because it's in the first column on the periodic table, has 1 valence electron. And we said that usually metals are looking to get rid of their valence electrons, whereas nonmetals are looking to pick up valence electrons. Does that all sound somewhat familiar? Okay. Now, that being the case, that's why metals make good conductors. Conductors allow current to flow through them. Current is the movement of electrons. We introduced that yesterday. Metals are looking to lose their valence electrons, so they don't hold on to their valence electrons very tightly. What ends up happening then is that we end up, like it says here, electric charges move freely within a framework of protons. If this dot represents an electron, a valence electron, and we'd say, okay, this valence electron belongs to this atom. But really, that's not exactly the case. This atom doesn't want this valence electron. So if it can lose it somewhere, it will. And what ends up happening is all of these valence electrons that are here, they don't necessarily belong to any one atom. They can kind of like flow in these spaces here, and they can go in this space here, and maybe they're closer to this atom at certain times, and maybe they're closer to this atom at other times. That allows, in certain instances, that charge it to flow from one side of it to the other. Okay? Does that make sense? The idea that metals don't want to hold on to their valence electrons, so they can kind of have the freedom to move about anywhere that they want. Good? Okay. On the other hand, insulators, if metals make good conductors, nonmetals make good insulators, because nonmetals are looking to gain electrons. Remember, we talked about halogens, right? Halogens have 7 valence electrons. They're looking to pick up 1 more. That being the case, atoms or nonmetals that are looking to gain electrons don't give up electrons easily. They're looking to pick up more, not give up ones that they already have. And because of that, that doesn't allow those electrons to flow easily from one atom to the next, which is what current is. Okay? Good there? Does that make sense? Right? So metals make good conductors because valence electrons, they're looking to get rid of them. And so they can just sort of like flow around in between the different atoms. But nonmetals make good insulators because they're trying to hold electrons tightly and they don't allow them to move. And if they don't move, that's no current. Okay? Good there? So that brings us back then to the outline that we were working on the past couple days. Right? We talked about voltage. Voltage deals with energy. Current deals with the number of electrons. But like I said, there's one more piece to that puzzle, and it's resistance. So, all right. By definition, so this is the one that has the ball on the very front page. We're like on page 3 right now, maybe page 4 actually. So, our last page. All right. So by definition, resistance is the impedance to charge flow through a material. That's a fancy way of saying how hard is it to make charges move through that material. So the impedance to charge flow. Some materials allow charges to flow more easily than others based on the previously stated factors. Those previously stated factors being how tightly do they hold valence electrons. That's really the determining factor whether charge flows through something easily or not very easily. Rachel, go ahead. The stated factors being how tightly will atoms hold valence electrons. That's the real key determining factor. Atoms that, like metals, that are looking to get rid of valence electrons, allow those electrons to kind of pass from one atom to the next pretty easily. Okay? But nonmetals that are looking to gain electrons, they hold on to electrons much more tightly, so they won't allow those charges to flow. Does that make sense? So, yeah, the previously stated factors are kind of like, how tightly does it hold valence electrons? Okay. All right, good there? Okay. Next section on your outline is factors that affect resistance, right? Okay. Don't worry about that. I decided not to include that on this outline. So that whole section right there, the 4 factors that affect resistance, you don't have to worry about that section right there. You can just cross it off. You won't be responsible for that. All right, so measuring resistance. Resistance is a relationship between voltage and current. So you'll see a little bit farther down in your outline, you have R equals, and there's a blank fraction, V over I. You don't have to include the delta if you don't want to. You can just go V over I, okay? So resistance is a relationship between voltage and current, okay? So resistance is a relationship between the applied voltage and the resulting current. Remember, voltage is energy, current is how much those charges flow. It would make sense that the more energy we give them, the more the charges flow. So more voltage is more current. But sometimes resistance plays a role in that. Okay. That good? I stands for current, V stands for voltage. So this fraction here, R is V over I, that's basically that's representing this statement here, that resistance is the relationship between voltage and current. Okay? Yeah, this is just a mathematical relationship of this statement. So it makes sense that the more voltage you have, the more current that you get out of it. But that's not always the case depending on the material itself. We can apply the same voltage to 2 different materials, and we might not get as many electrons flowing through one as we do the other one because of the whole resistance idea.
But like, if like the resistance ends up being higher,
Yep.
like would it be more likely that like the material is insulated?
Very much so. Yeah, if the resistance is higher, that means the material is more likely to be an insulator, right? Because it's harder to flow charges through that high resistance material.
So that, like, say like the voltage and the resistance or not resistance, or both lower, then it'd probably be a conductor.
Yeah. Yeah, that if we get low voltage and we get a low current out of it, right? That the relationship is there, but yeah, if we don't have to apply a whole lot of energy, but we get a lot of current out of it, that's a low resistance, right? Like low voltage would be a low number on top of this fraction, but a high current on the bottom. If we have a small number on top of a bigger number, that's a small resistance. Does that make sense? Okay. Yeah, so that's how easily does that charge flow through that material. We use the SI unit of the ohm to represent resistance. Ohm is represented by a capital letter omega. Kind of looks like a horseshoe. All right, good there? Don't worry about the one on the far right that says 1 ohm equals. Well, don't worry, I won't hold you responsible for that. So you can cross that out. That's good. All of this comes together with something we refer to as Ohm's law. Okay? Basically, we just take that equation, that fraction that we had written down, rearrange it, put voltage by itself. So you're basically multiplying both sides by R. Or sorry, both sides by I. And you end up with V is equal to IR. Voltage is equal to current times resistance. This is how all three of these things come together to determine how much current do we actually get through this material, taking into account how much energy we've given the charges, the voltage, and the resistance, how hard it is to get those charges to flow through. Okay? Somebody in the previous class made a statement that, so does that mean every object has resistance, some just have more resistance than others? And the answer to that question is yes, that's a pretty true statement. But there are some materials that we can effectively make have no resistance. And we refer to those as superconductors. Okay? And I think that shows up at the bottom of your page, but it's nothing really to write down, right? So, below certain temperatures, some materials have the ability to conduct current with no resistance. This is a situational thing. There are no such things as superconductors that exist all the time. It's based on certain conditions, okay? I want to show you guys just a short little video to illustrate this concept, okay? So I'm going to stop the recording because when I record streaming things, it makes the recording really long. So I'm going to pause this, and we'll come back in a little bit. All right, we're back, everybody. So, last part of the unit on electricity deals with electric circuits. And I think, again, it's probably a term that you're familiar with, something you've heard before. Let's talk about what it means. So like the little tagline says, what can we do with these flowing electrons? We know these electrons have energy, electric potential energy. Energy is the ability to do stuff. Well, what do we do with it? Well, it depends on how we set things up, and that determines what we can do with it. So, first, definition of a circuit. A circuit is a set of components connected to provide one or more complete paths for the movement of charge. Remember, batteries are voltage sources. Voltage is energy. So as charges flow through the battery, they gain energy. But something that gains energy is ultimately looking to lose it in whatever form. turning that potential energy into other forms of energy. A circuit has to contain a voltage source or a source of energy, something to increase the energy of the charges. But then the circuit also provides a path where the energy that the charges gained by going through the battery are then turned into other forms of energy, whether that be light, like in a light bulb, or heat, like in a toaster, or sound, like through a speaker, right? All of those things are ways that the charges that go through the battery and gain energy can ultimately lose that potential energy into other forms. So that's really what a circuit is, a way for those charges to gain energy and then for us to use that energy by turning it into other forms. That's the circuit. All right, it's good? Okay, so let's talk about three terms that we talk about when we talk about circuits. So first, closed versus open. A closed circuit is a complete path of conductors so that charges can flow from high potential energy to low potential energy. A closed circuit is a complete path. Right? This picture we saw when we were talking about electric potential energy and current, right? We said that as charges move through the battery makes them go towards the negative terminal. It does work on them, right? But they don't like being at the negative terminal, so they want to get back all the way over to the positive terminal, right? But they have to have a path to get there, a path of conductors. If it's a complete path, that's a closed circuit. If there's a break in the path, we refer to that as an open circuit. If there's no path for the charges to get from the negative side to the positive side of the battery, there is no current. So open circuits have no current. And then whatever is in the circuit, like this light bulb, doesn't work, because the light bulb has to take potential energy and turn it into other stuff. If it's not getting charges that have potential energy, it won't be able to turn it into the other stuff. Laura, go ahead.
So when like you flip a light switch, is it just completing the circuit?
Yeah, or breaking the circuit depending on which way you're flipping the switch. Yep. That a circuit or a switch, if we go back to this one. This one has like a switch built into it, right? Yeah. Sometimes, right, a circuit is turning potential energy into other stuff, like a light bulb turns electric potential energy into light. Sometimes we don't want that to happen, like we want the room to be dark. So all we do is we break the path for the charges to flow, and then it doesn't happen anymore. So yeah, a switch is just a purposeful break in the circuit, right? Because sometimes we don't want those charges to flow. The last thing we talk about is sometimes is a short circuit, right? A short circuit is a result of the fact that all of the energy that the charges gain by going through the battery, they have to lose into something else. Light bulbs turn electric potential energy into light. Toasters turn electric potential energy into heat. Remote-controlled cars turn electric potential energy into the movement of the car. But if there is very low resistance, right? If basically there's no light bulb or no heater or no anything in there, that electric potential energy basically just turns into kinetic. The charges move really fast and it becomes hot. Okay? So, with very low resistance between the terminals of the voltage source, the current is very high. Lots of movement, lots of kinetic energy means lots of current. Lots of current means charges going past really, really fast. That causes things to get hot. And that's when we have things like fires and melted wires and things like that. Okay? So with very low resistance, there's a lot of current. And a lot of current means a lot of heat. Okay? Good there? All right. Let's talk about two types of closed circuits. The first one is a series circuit. A series circuit is a single path of conductors. There's only one way for the charges to flow. Remember, they're trying to get from one side of the battery to the other side of the battery. In a series circuit, there's only one way for them to go. Go good. Because if one of them goes out, there's a break in the path and the current stops. Yep. So Dylan, that's exactly. If there's a break in any part of this path, the current stops in the whole circuit. Okay. Very good. Yep. Christmas lights that are put in series. Yeah. If you have one out, they all go out because there's only one path for the charges to flow through the Christmas lights. Okay. All right. On the other hand, we'll get back. We'll fill in the rest of the stuff on series circuit. On the other hand, because you guys are going there, okay, there's parallel circuit. Okay, I said we're going to skip some things because I thought the conversation would flow better this way. Okay, so with a parallel circuit, there are multiple paths for current to flow. So parallel circuit's on the back side of the paper, right? So with a series circuit, there's only one way that the charges can go. Remember, charges are looking to get from one side of the battery to the other side of the battery. Okay? Let me zoom in here on this picture so you guys can see it a little better. I believe you guys have both of these pictures, yes? Okay? So, the one on the left shows the bulb sort of connected together to the battery. The one on the right is called a schematic drawing. A schematic drawing is just a representation of how the things are connected. So, this little symbol right here, one line short, one line long, that represents a battery. So that's representing the battery in our picture, okay? Schematics are going to show up here over the next couple of days. So, one short line, one long line, that's the battery, okay? Squiggly lines with circles around them, those usually represent light bulbs, okay? Pat, good. Usually it's just gonna. You'll have to know battery and you'll have to know light bulb. That's about it. So yeah, this is about as complex as we're gonna get as far as schematics go. We won't get into like diodes and things like that. So a switch is usually just kind of like a break in this line. You know, like we'll kind of like, yeah. So, all right. So you'll see on the battery one short line, one long line. The long line has the positive symbol right there, right? That means that the battery forces electrons over to the short side, and it pushes them out into the circuit that way. So all the charges flow out, they come down here, they come across, and they hit this junction. Some of them go to this light bulb. But there's another way that charges can flow. They can go through over here. They hit this junction, and they have another choice. Any way that they go, they start on one side of the battery and they end up on the other side of the battery. That's important. Steve, good. No. That's a good question. Stephen said, with this first light bulb, because it's the closest, right, would that be the brightest? And the answer to that question is no. As long as all three of these light bulbs are the same. Okay? Because remember, we're talking about electrons that are moving, right? They're trying to get away from the negative side of this battery, but they're also trying to get away from each other as much as possible. Does that make sense? Because they're all negatively charged. So you won't have more electrons going through the first light bulb than the second or the third, because that means they wouldn't be nice and evenly distributed. They will try to distribute themselves out as evenly as possible. So the answer to the question is, each one of these light bulbs would be exactly the same brightness, because all the electrons that come out of this battery try to distribute themselves as evenly as possible. Say again? Is it like a law? Yeah, basically. It's kind of like conservation of charge, but we get into the idea of like even going back to like Hund's rule, right? Electrons try to distribute as evenly as possible. Same thing's true here. If there's more ways to go, they will choose to go that way, right? Think of it like a checkout counter at Target or the grocery store, right? If there's only one register open, everybody has to go through that register, right? That's a series circuit. Everybody's got to go the same way. And as a result, what ends up happening? It takes longer. It's slow going, right? But if we open up more registers, what do the shoppers just naturally do? They distribute themselves out as evenly as possible usually, right? There's no reason for you to wait in a line that already has 3 people in it if there's a line that only has 1 person in it, right? Same thing with electrons. They won't back up. They'll try to distribute themselves out as evenly as possible, okay? But something to keep in mind, regardless of which path they go, they always have to have a way for the electrons to lose the energy that they've gained from the battery. Each one of these light bulbs is individually connected to the voltage source, to the battery. And that allows all of them to lose to lose the energy that they gained by going through the battery originally. Okay? Good there? Good for starters? Okay, let's go back to series circuit. So, all right. When we have a series circuit and there's only one path for the charges to flow, the current in every part of that series circuit will be the same. So Stephen, kind of like we just talked about, you won't have more current by one light bulb than another light bulb because all those electrons are trying to distribute themselves out as evenly as possible. So current is the same in all parts of a series circuit. And if you add more resistors, if you add more things in the circuit, that's going to slow everything else down, right? Kind of like at the airport, right? Anybody ever been to the airport recently? Like you go through security, but then there's like one person that has like 4 pennies in their pocket, and they have like their belt buckle, they didn't take their belt off, like, and so they go through the little X-ray scanner machine, okay, but then they have to stop, and the agents are like, do you have anything in your pocket, you know, even though we told you to take all that stuff out of your pocket to begin with, right? It just slows everything else down. But
my grandma has like a metal like thing in her knee, so it took like half hour to 45 minutes to get through it.
yeah, they're weird about that kind of stuff, you know, like. I suppose if it's a matter of blowing up the plane or not blowing up the plane, they probably should be careful about it, you know. So, but. When we talk about adding more and more light bulbs, we talk about the equivalent resistance, or what is the total of all the resistance. In series, all we do is just add up all the resistors. So, Req, the equivalent resistance, basically takes the resistance of one light bulb plus the resistance of the second light bulb plus the resistance of the third light bulb and just adds it all together. Okay? Good there? So when we talk about adding more and more light bulbs or more and more things in that circuit, we increase the resistance of the whole circuit. Devin, go ahead. Yep, squiggly line is just a generic thing for resistance. A light bulb is a resistor. It's just a specific kind of resistor that turns it into light. That's why it's a squiggly with a circle around it. All right, good there? Okay.
Yes.
For parallel circuit, okay, on the back, okay, so it says the voltage across each component has to be the same for all parts of the circuit. Okay? So the next thing you have so parallel circuits back on the other side. And basically what that means is that no matter which way those charges go, all the energy that they gain from the battery, they have to lose somewhere. Okay? And that means that, so Stephen, we said that will the current be different? The current will be the same as long as all three of those light bulbs are the same. But if one of the paths in a parallel circuit has more resistance than the other paths, it will have less current because it's harder for charges to get through there. So if all the paths are the same resistance, they spread out nice and evenly. But if one path is easier than the other path, more people will go there, right? Like when you go to the grocery store or if you go to Target, right? If you see a checkout, if you see like a register that has an older male working the register, go to that one, okay? Because old guys, they don't care about your day or they don't care about like, what you're doing. They just are just like beep, 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 here we go, right? They don't ask questions. They don't want to know anything about you. They don't want you to know anything about them. They're just like, let's go, right? Old ladies, though, right? Old ladies like, oh, it's so cold out today. Make sure you bundle up when you go out, So if you have the choice, go to the register that has the old men as opposed to old ladies, all right? It's kind of like my public service announcement. Not that the old ladies aren't nice, right? But if you're looking to get out of the checkout line quickly, yeah, old guys don't ask questions. They don't want to know anything. They don't want you to know anything. Just here we go. So. All right, good there? What were you writing down when I was talking about the old ladies and the old men? So, 2 key points. 1, no matter which way we go, charges have to lose all the energy that they gain from the battery. And 2, if the resistance of each section is the same, the current will be the same. But if resistance in one part is higher than other parts, it will end up with less current. All right, good there? So, for tonight, there are some questions about circuits on the calendar. Tomorrow, we will do a couple more examples and finish up the circuit thing. So if there's some things on the outline we haven't filled in yet, we'll get it tomorrow, okay?